All right. So this is the you know lecture I promised you to post. Okay, so this lecture is about solving some of the problem from chapter 5, and then there will be another lecture where I'm going to discuss a little bit about the chapter 6. Okay. All right. So please watch these. Okay. All right. So some of the problem we already solved, and here I'm going to do the rest of the problem. Okay. Now let's start with number 5. Okay. Problem on banked curve. Okay. So remember that I already told you there will be one question on highway curve. It could be from banked, I mean a flat or unbanked curve, or from banked curve, or from both. Okay. All right. So what we are given here, we are given the radius of the curve, and then it says that the speed. Okay, so the speed is given in kilometer per hour. We have to calculate the bunking angle. Okay, so you know that to calculate this, we have to actually first derive the equation. You know that this equation is not given in the list of equation. So what you have to do, let's go to what you have to do. Yeah, so this step we have to do. Yeah, you know that I mean, we already did in the last class, right? So you already know that, right? So here you see that a banked turn, and this is the cross-sectional area. Okay. So gravity downward and the normal force perpendicular to this ramp. Okay. And then here you see that this normal force you break into two component, cosine theta. So this is the cosine theta and cosine theta, and this is n sine theta. Okay, so we have also friction, but for simplicity, we actually ignore the friction. You know, if we include the friction, this calculation will be little bit complicated than what we have here. So that's why I actually ignore the friction. Okay, and introductory algebra based physics, we actually always neglect the friction. Okay, so simple. So here you see we have these components, and here out of these components you see that the normal force has two components, and yeah, gravity is downward, and this one is balanced by these, right? Mg is balanced by n cosine theta, right? We already see that, and this is balanced, we can say that because there is no other force acting in the vertical direction. So that's why we can say that mg is balanced by n cosine theta. So here you see this part tells you that. Okay, and here I actually started from the Newton's second law, y component, and because there is no acceleration in the y direction, I use the right hand side is equal to 0, and then I solve it. I got this. The same thing, n cosine theta is balanced by mg. On the other hand, you see that this component is toward the center of this curve, right? So that means, the centripetal force is actually provided by this component and sine theta, right? So here you see that in this paragraph here. Okay. And then what I did is basically, we have two equations, okay, and do little bit of math, algebra, right? So in this case, what I did, I actually, yeah, divide this one by this one and got tan theta. The tan theta is equal to n sine theta over n cosine theta. N sine theta is this equation, right? And cosine theta is the first equation. And then I plug these values. And this gives me this equation, right? And then theta is equal to tan inverse V square over RG, right? Now let's go to the solution. Okay. So here you see, because the speed is given in kilometer per hour. Okay, so here you see, we cannot plug this value in the equation because it is not standard international unit, right? So we have to convert it into standard unit. So here you see that how I convert. Okay, so I get 55.6 meter per second. Okay, so kilometer, 1 kilometer is 1000 meter. Okay, so remember that these are the things we use. 1 kilometer is 1000 meter, and 1 hour is 3600 second, right? So 200 kilometer per hour, if you want to convert, you have to, kilometer, 1 kilometer is 1000 meter, so kilometer cancel out, hour, second, so 1 hour is 3600 second. So here you see, kilometer cancel out, hour cancel out. And then if you do this math in your calculator, it should be approximately equal to 55.6 meter per second. Okay, and here you see that we have the same value. Now, so this is the equation, right? We derived, you know, in last class, also today here, right? So you have to calculate tan theta, theta actually, right? So if you plug all these value, so V square is 55.6 square, right? So this is tan theta. And then R is 75 and G is 9.8. So this is approximately equal to 4.20. Theta tan inverse 4.20 is our answer. And that is approximately equal to 76.6 degrees. Okay? So that's how we should solve this problem, bunk problem. Now, in some homework problem, you will see that instead of asking or calculating the theta, the bunking angle, I ask you to calculate V or R, right? Then you have to, solve for V or solve for R. Okay, but this is the equation, tan theta equal to V square over RG, and whatever you need, you have to, solve for it and plug the values. Okay, all right. Let's move on, and then let's do number 6. Okay, number 6 is, okay, so number 6 is this one. So at the topmost point of the London Eye, a renowned Ferris wheel with a diameter of 120 meters. Okay, how many revolution per minute would it need to make for passenger to experience a sensation of weightlessness? Okay, so 3 things here very important to, we have to carefully read it. Okay, so the first one is it gives diameter. Okay, and none of the equation we have in this equation use diameter. All the equation we see in this chapter for acceleration, for force, it involves the R, the radius, right? So if I give you diameter, make sure you convert it into radius. you divide by 2 and get the radius. Okay, so diameter is given to 120, that means the radius is 60. And then it gives okay, so it says that passenger experience a sensation of weightlessness. Okay, what it means. And also it asks us to calculate what? How many rep per minute. Okay, what it is. Okay, so how many rep per minute is basically the frequency. So it asks us to calculate the frequency. But you know, the frequency regular unit is rep per second or hertz, right? Turn per second or revolution per second or cycle per second, which we call hertz. Here it asks us to calculate RPM. Okay, so that means it is frequency. And the third thing is weightlessness. Weightlessness means, remember, it is Fn equal to 0. Okay, all right, so remember this. Now let's go to the solution. Okay, so let's say this is our Ferris wheel. The topmost point is here. Okay, so to feel sensation of weightlessness, normal force needs to be equal to 0. Okay, so that means if normal force is equal to 0 for weightlessness, okay, now we have two forces. I mean, actually, one special force, that is mg, and it is toward the center. So that means this mg is also the centripetal force. So that means this gravitational force, is actually providing the centripetal force. So that means they are equal to each other, right? And we know the centripetal force is equal to Fc equal to m v square over r, and gravitational force is equal to mg. So that means this is equal to this for the sensation of weightlessness, right? Now here you see that some of the, so here m cancel out, right? So this tells us that v square r equal to g, or v square equal to r times g, or v equal to square root of r times g, right? Okay. Now, what is this value? So we already know that r is equal to 60 meters, right? 60 meters. And g is equal to 9.8, right? This tells us that the speed of the Ferris wheel is equal to, so if you plug these values in your calculator, you should get this value, 24.2 approximately. So 24.2 meter per second, right? Now, it tells us to calculate the frequency, not the speed, right? So that means we have to find the speed's relation to the, frequency's relation to the speed. And we already know that that is equal to 2 pi r f. So f should be then equal to v over 2 pi r, right? I divide both sides by 2 pi r and I get this, all right? So v is 24.2, 2 pi is 2 pi, and then r is 60, right? So this is the frequency um, in second, rep per second, okay? So here you see this is the number. You know, if you plug these values in your calculator, you should get this value, 0 point, so 0.0643 reb per second. Okay, but we have to calculate the number in RPM, right? So this is number per second. You know, the number per minute will be higher, right? How much higher? So to get that number, we have to multiply this number by 60. Okay, you know, rev per second. Now we want to, the remove second. We want in minute, right? 1 minute is 60 seconds. So that's how, that 62 on the top, right? So when you multiply these two, you get this value, 3.86 RPM. Okay, so the correct answer here is 3.86 RPM. Okay, and here you see that how the second and second cancel out, right? So now it is rep per minute or RPM. So the answer here is 3.86 RPM. Okay, so the revolution per minute is 3.86 RPM. All right, let's move on. All right, so the next one. Yeah, so we already did number 7. Let's do number 8. Okay, number 8 is very similar to number 7. Okay, so here it asks us to calculate the gravitational force, similar to the gravitational force between the girl and boy in number 7. Okay, so here only one thing you have to understand is it says that, um, okay, so satellite orbit, the distance from the center is this much, 1.5 times the radius of Mars. Okay, so that's what that I mean that important information. Many students actually make mistake here. So that is important information. Once you understand this, the other thing is straightforward. One more thing is many students actually forget that kilometer is not a standard unit. 1 kilometer is 1000 meters. In the last class we did several problem, and in all the problem we had to use 1 kilometer equal to 1000 meter or 10 to the power 3 meter. If you don't plug it, you will end up with incorrect answer. So when we calculate the planet or satellite, and if there is a number in kilometer, make sure you convert it in meter. Okay, so here, yeah, that this number we have to convert into meter. All right, so let's go to the solution and solve there. All right, so this is the equation, right? Gravitational force, the Newton's laws of universal gravitation. Okay, G will be given in your list of equation. So it is this. Okay, planet mass is 6.39. The Mars's mass is this one. Okay, and the satellite mass is 1500 kilogram. Okay, and the radius, the from the center of the Mars to the orbit where the satellite is orbiting. Okay, that distance is 1.5 times the radius of Mars. So 1.5 times this is given, and kilometer, so it is in kilometer, you have to convert it into meter. So that means whatever you have here, you have to multiply by 10 to the power 3. Okay, that gives you this much meter, right? So now let's plug these values. Okay, so this is our equation. Fg, so 6.67 times 10 to the power 11. M1 is the mass of Mars, so this is this one, 6.39 times 10 to the power 23 kilogram times um, mass of the mass of the satellite, 1500 kilogram. So these three number will be in the top, and then denominator will be these. Okay, so how we get? We get 1.5 times the radius of Mars. Radius of Mars is given to, this value 3390 kilometer, 3390 kilometer. So in kilometer, the total distance from the center to the orbit to the, position of the satellite is 5085 kilometer, but we need in meter, right? So then we multiply this number with 10 to the power 3, and that gives us this number. So if I plug it here, so 5.085 times 10 to the power 6, and then square. Do not forget this square. From my experience, I can tell you many of the students forget this square. Okay? And then you see that this time we have significant value. Okay, 2472 Newton, 2472 Newton. Okay, and that's because we have a big planet, right? So because of this big planet, these satellite actually feel that force, and this force actually helps this satellite to orbit around the planet. Okay, all right. All right, so the rest of the problem we actually solve when we discuss the theory. Okay, so I'm not going to do the, I'm not going to solve the problem, but I'm going to tell you what equation, how to, what equation for what again. Okay, all right. Okay, number 9. Okay, it asks us to calculate G, okay, at at an altitude of 550 kilometer above the Earth's surface. We already calculated a similar problem for the ISS. What is the value of gravitational acceleration at at the altitude where ISS orbit, right? So that time we use 420 kilometer. The same thing, okay? So how to solve this type of problem? Again, remember that these equations are not in the list of equations. So we have to derive, you have to, understand how to get this equation, right? The two equation we discuss, and they are this. Gravity is equal to mg, right? And then gravity is equal to g m r square, right? They're the same thing. So if you want to calculate gravity, then we have to, the equate these two. Okay? And you see m and m cancel out. G equal to gm r square. Okay? Now this equation, we use two different way. One, at the surface. If you want to know the gravitational acceleration at the surface, then G is equal to gm over r square. Then we have to use just the radius. Okay? And another is at some altitude. Okay? This time our equation is this. Okay? So here r is the radius and h is the altitude. So do not confuse between these two. Okay, so for this problem, number 9, okay, we have to use the second one, the green one. Okay, because the orbit is 550 kilometer from the surface of the planet. So that means h is 550 kilometer. Okay, all right, so that's one thing. And then for number 10 we will be using the blue one. Okay, so it asks us to calculate the gravitational acceleration on the surface of moon. Okay, and the information for the moon's mass and the radius is given. So just plug those values. So important thing to understand is, if it is for the surface, we'll be using this one. If it is at some altitude, we'll be using this one. Okay, all right. Now the last one, also we already did it for International Space Station. Okay, so this is for another satellite. Okay, but the procedure is exactly same. Okay, so that's why I'm not going to numerically calculate this. Okay, but let me tell you how to solve again. Okay, so again, the equations are not in the list of equations, so you have to understand how to derive this equation. Okay, so Fg here is equal to G m m r square, gravitational force, and centripetal force is m v square r. They are given. This, both of this equation, and even I think this is also in the list of equation. Okay, so in this case we don't need this for 11. Okay, when we need to calculate v, we need these two equations. Okay, so when a satellite orbits around some planet, the gravitational force is actually the centripetal force. The physical force here is the gravitational force, and this act as a centripetal force. So that means we can equate them together. I mean, we can equate these two equations. So we can write m v square over r equal to g m m r square. And again m and m cancel out, one of the r cancel out. So here you see v square is equal to g m r, or v equal to square root of g m r. And in this case, g m r here is r, the radius, plus the altitude. Okay, so remember that. So now we have to plug all these values here to calculate v. Okay, and then time period, the time period we calculate from v equal to 2 pi r over t from this equation. So once you know v, then we already know r. Then plugging the values here, we can easily calculate t. So t is equal to 2 pi r over v. And remember that 2 pi r is r plus h. Okay, so yeah, that you have to keep track. This small r is not just a single number. It's like a sum of the radius plus the altitude. Here you see that altitude is 450 kilometer for this Chinese space station. Okay, and today we derive another equation, from this equation basically, for the time period, right? So you can also use that equation, I think, given in the list of equation. Okay, so that's it for this chapter. So we are done with this chapter. Okay, I'm also going to post some theoretical part for chapter 6. Okay, all right.